Hey, and I am
I have a couple of questions.
putting my ears in.
Okay.
Sorry.
Okay, I have a couple of questions.
Okay.
Okay, so I took the quiz this morning and I understand that uh I looked over the PowerPoint and there's some I didn't know some of the answers and you
Okay.
didn't.
All right. Let me stop you right there. Okay. The quizzes are designed half and half. 5 questions are going to be on what I covered. 5 questions are going to be fairly easy on what I'm going to cover. Okay. Does that answer your question?
Yes, but and I wasn't sure about some of them. Even when I looked over the PowerPoint, it was more of like when I look back, I don't know. And I know the answers aren't gonna be like right there in front of my face, but
Let's
it may
look at it. Okay.
okay.
Do you mind if I pull up? There's nobody else here. Do you mind if I pull up your quiz on share screen?
No, I don't.
Okay, just with the caveat that somebody may join the meeting and okay. Okay, courses. By the way, are you Anaya, are you familiar with the course as it's designed?
Um,
That would be
no, but
enough.
I have taken chemistry 2 before and I did not pass.
Okay. Well, good. At least you have some sort of a foundation.
Yes.
Okay, by the way, I'm sorry that we got off on the wrong foot. Um, it's just that I've had other students that have said, "Oh, Mr. Popovich, I'm going to miss 2 weeks of the summer course. Uh, deal with it." And that's like a quarter of the course, and they don't realize that, yeah, that they're not
I
signing up.
under I understand where you were coming from. I didn't know that your class was online because when I signed up, I thought that I had signed up for your in-class lecture. That's why I was confused. But
That,
then
that
I saw that it was all online and I was like, okay, I can do this because I'm still at school in
sure.
Georgia. We're going to regionals. So like we'll be
Good
done
luck
by
with that.
thank you so much. I didn't
Good
think we'd be
luck with that.
but yeah, so yeah, but this is cool because this way we can kind of go over what I might need help with. So yeah.
Okay, it was quiz 1.
Yes.
I need to get off of here. Okay, I'm not going to bother going over the ones you got right. Okay.
That's fine.
All right. This is a straight up thing.
Okay.
Okay, straight up answer. Okay. This is the first slide that I'm going to go through today in my PowerPoint, and no, it's not the first slide I'm going to go over. It's a review.
Okay.
I went straight through the rankings of the intermolecular forces. Dispersion are the weakest. Dipole are next. Hydrogen bonds are kind of like super dipole bonds.
Okay.
So which has the greatest power? Hydrogen bonds are going to have that greatest power. I'm sorry, I'm waiting for a question. And
I was gonna ask why.
why? All right, because by the way, somebody's coming in.
Okay.
Just be aware of it.
Okay.
Why? Because when you have a hydrogen bond, you have 3 elements: uh,
Nit-
fluorine,
nitrogen.
oxygen, or nitrogen.
Okay.
Okay. Now, those 3 elements are the 3 most electronegative elements that exist.
Okay.
So what happens is they pull more of the electrons towards them, and their end is more. It's like they're almost an ionic bond.
Okay.
So they really pull that those electrons away from the hydrogen, making a real strong positive end and a real strong negative end.
Okay.
That's stronger than dipole-dipole.
Okay.
Okay. Guys, Jana, again, I'm sorry, Anaya, I've got a whole bunch of people that are logging in. Do you mind?
No, you can continue.
Guys, I've had questions about the quiz, so I'm just going through and answering them one at a time. Dispersion forces.
Okay. For this one, I actually answered the wrong question because I know that they are I meant to click all answers. Yeah. So this one was a goof on my part.
Okay. All right. Anytime you break a bond, break an interaction, it's an endothermic process. You have to, if you didn't put energy in, it's going to stay the way it is. Right, Anaya?
Yeah.
Does that make sense to you?
Yes.
So when you are breaking these interactions, you have to put energy in to do that. That is an endothermic process.
Okay.
By the way, anybody else can jump in if you have a question. Okay. Heating ice to steam. It is an endothermic process because don't you have to put energy in to ice to make it liquid? Then you have to put more energy in to heat it up to be steam, right? If you're putting energy into the system, it's endothermic. This is true. This is a true statement because all the energy, when you have ice and you're taking something from ice to water, all the energy is going in to breaking the intermolecular forces, which is making it ice. So all the energy is going into breaking those forces that make it ice. Then once we've gotten all liquid, then the energy goes to raise the temperature.
Can I stop you real quick? I don't think this is my
I was
quiz.
stopped. Go ahead, Anaya. I'm sorry.
I don't think this is my quiz.
Oh,
That's why I'm kind of confused.
okay. Sorry.
It's okay.
Anaya, your last name?
Rasul, R-A-S.
Gotcha. Sorry.
Yeah.
I apologize for that.
Yeah.
Okay.
Here we go. This is what I need.
All right. Now, each one of them have an H attached to an oxygen, right?
Okay.
So each one of them have a contribution, a hydrogen bond contribution, right?
Okay.
The thing about it is, if you have a larger molecule, larger molecules have larger electron clouds. So larger molecules have larger intermolecular forces. Okay, does that make sense to you?
Yes.
All right. Since it has a bigger force, its tendency is going to want to make a solid. Does that make sense to you? And if its tendency is going to want to make a solid, the freezing point is going to be highest for butanol as opposed to methanol. Okay, I'm going to go back. And no, I'm not going to. I'm not going to change it. It is the way it is. It's propanol is not it's kind of in the middle.
Okay.
Okay.
This is what I was confused about because, like you said, you just told me half is what you're gonna talk about then, but this was kind of hard, and I wasn't really.
It was a hard question.
What it was, the answer was.
It's a hard question. This is one of my thinking questions. You're going to have to learn, Anaya, that basically in this class, I'm going to do a lot of questions where you have to interpret what is happening in the equation. Okay? And I'm going to show you how to do that in a second. All right. If it decreases from T1 to T2, is T2 less than T1?
No.
It decreased. I'm sorry. Yes. I'm an idiot. Yes. T2 is less than T1. Right? So in terms of sign, if T2 is less than T1, what is the sign of 1 over T2 minus 1 over T1? Is that going to be positive or negative?
Positive.
Okay, because this number, because T2 is less, this number is going to be bigger than this one, right? So I've got a positive fraction multiplied by a negative, correct? So if I've got a positive by a negative, the right side of the equation is negative, right? All right, now you got to think, how do you get a negative log?
I'm not sure.
You get a negative log by having a number less than 1.
Okay.
If you have a positive log, it's a number greater than 1. All right. So I have a negative sign over here. This means that my log must be less than 1. If my log is less than 1, what is greater, P1 or P2?
P2.
P2, I'm sorry, which one is greater? If the ln has to be less than 1, so is P2 bigger or smaller than P1?
Smaller.
P2 is smaller because it's less than 1.
Okay.
All right. So if P2 is less than P1, then the pressure decreased.
Okay.
And this is a very much a thinking question. This is very much the type of interpretation you're going to need to do, because MCAT questions are questions like this. If you go and do the chemistry Olympics, they're going to give you questions like this. Yes, they're hard questions, but you got to logically work your way through them.
Professor, I had a
Yes,
question.
sir. Yes, sir.
On question 4, did you say that butanol should have had the highest freezing point?
Yes.
Because when I picked that one,
Did
but
you
it told
look
me
at it? Did you look at it? Let me shut up for a second. Ask your question.
because when I picked it, it told me it was wrong
When did you pick it?
yesterday.
Okay. Did you look at your score recently?
No, did you change it?
I changed it.
Oh,
The
I will go
answer
check
was
that.
originally wrong.
Okay.
If you took the quiz after I discovered the error, then I had put the correct answer in there.
Okay, sorry, my bad. I'll go look at it now.
Now, what is your name?
Parker Herdenstein.
Parker, I will look. I believe I did correct it, but I will go back and check.
All right, thank you.
Wait, I'm sorry. What was the correct answer?
Butanol.
Butanol? Okay.
Yes.
The same thing. All right.
And I answered this question earlier.
Yeah, I just wasn't sure about it because I know that when it's doing the change, there's no change in temperature, but when it's
within a phase, you
Yeah.
can raise the temperature. If you're going from one phase to the other, if you remember the heating curve line, slanted line, flat line, slanted line, flat line, slanted line.
okay.
All right.
All right.
While I'm in here, does anybody else have any questions
Professor, I have
about
a
the
quick
quiz?
question. I have a quick question. If we did get that propanol question wrong, do we just email you in case you haven't changed it?
That depends. When did you answer the quiz, Natalie?
The 18th.
If you were early, then I did change the answer yesterday. So it should be correct. If you still have it marked wrong as butanol, then, yeah, let me put it that way. I'll throw it out there. If you look at question 4 and you answered butanol and it's marked wrong, bring it to my attention. I will correct it, okay? That's the easier answer. I believe I did correct it though, Natalie.
Okay, thank you.
Question, somebody else had a question.
Yeah, I don't think you did correct it because I took the quiz like 20 minutes ago and I put butanol and I got it wrong.
Okay,
Yeah, same.
Sam. All right, first person, who was it?
Sam,
Sam. Okay, Sam. Sometimes what happens is if I don't click the update question, it won't go in.
okay.
Sam, do you mind if I show it?
No.
Then I will go back and check them all. I will go back and check them all. Okay? Any other questions, ladies and gentlemen? You're all in here early. Good.
Professor, can you go over question 8?
Sure. I just went over that one. Okay?
I just got here.
All right. What you have to do, this is a thinking question. You basically have to interpret what's happening in the equation to be able to answer the question. All right. If T2 is less than T1, and that's what the question says, is 1 over T2 bigger or less than 1 over T1?
So T1 is less than T2.
No, T2 is bigger than, I'm sorry, T2 is less than T1.
They're both the same?
No. If T2 is less than T1, okay. Let's say T1 is 4 and T2 is 2.
Mm-hmm.
So you now have 1 over 2 minus 1 over 4, right?
Mm-hmm.
Is that number going to be positive or negative?
It's gonna be negative.
1/2 minus 1/4. 0.5 minus 0.25.
Oh, sorry. Yeah. Sorry, it's positive. Yeah.
All right, so this term, the 1 over T2 minus 1 over T1 is a positive number.
Mm-hmm.
I'm multiplying it by a negative.
Negative.
So the right side of the equation is negative.
Mm-hmm.
Now, you have to ask yourself, how do you get a negative log? Do you know that answer?
Not sure right now.
I'll throw it out to the company. Anybody know? Samantha, you got the answer right.
Yeah,
How do you get a negative log?
you have a negative. You have a number smaller than 1.
Absolutely. So if you have a number smaller than 1, you get a negative log. So the ln of P2 over P1 is negative. So P2 divided by P1 must be less than 1.
Mm-hmm.
So if P2 is less than P1, the pressure must have decreased.
Okay. Thank you.
And guys, that's the way you have to work through these particular problems.
Professor, I have a question.
I'm here.
For number 6, I emailed you about it. The slide that I found that answer on was slide 37.
All right. 37.
Yes.
That's what I said right here. It's endothermic. When you're breaking the dipole, the salt. Okay. All right. How do I explain this? Nope. Pencil. Okay. How I'm going to get out of this and is this is not talking about that. The slide doesn't pertain. I'm talking about solvent-solvent interactions and solute-solute interactions. Okay? What the slide is talking about is solute and solvent. Not solute-solute and not solvent-solvent, but it's talking about the solute and the solvent bonds. Okay? Zachary? Zachary? I'm sorry,
Yeah,
who's asking the
but-
question?
Yeah, me, Sachari.
Okay, so that's why the answer is what it is. When you break,
I guess it's just the wording that's confusing because the last paragraph on that slide, it seems almost identical to the question you asked. And it says this is exothermic and it says
but
solute,
it says
solute.
no, it says that is exothermic and it can overcome the breaking of the intermolecular forces between solute and solvent.
Mhm.
I admit that the slide is a little bit confusing. I'll admit that, and I'm going to go back and change it when I get the chance. And slide 37. But this slide does not directly relate to the question.
Okay.
Okay, guys. Little bit of review. Yes. Let me get this thing out of here. Little bit of review. We have 4 intermolecular forces. 4. Dispersion. Dispersion involves temporary charges. The electrons are on one side of the molecule or the other. That gives a temporary positive and temporary negative side of the molecule. That attracts other molecules like that. There are also permanent charges. There is an electronegative difference between the atoms. So one of the atoms holds the electrons more than the other one. If that's the case, then you have a dipole-dipole. It is a stronger force. Then you have hydrogen bonding. hydrogen bonding involve extra special, strong dipoles. You have to have one of three elements bonded to a hydrogen in order to have hydrogen bonding. It has to be hydrogen, nitrogen, oxygen, or fluorine. Okay? The last one is an ion dipole, and that's even stronger than hydrogen bonding because not only do you have a permanent charge, but it has the individual substance has all of that charge. So it's a stronger reaction. Dispersion weakest, ion dipole strongest. And you have to understand when you're asked a question, what is being involved? If you're asked something like, what is the highest freezing point? What you have to interpret that to mean is that the highest freezing point is going to occur among the molecules that have the strongest intermolecular forces. That's because they have a tendency to want to be solids anyway, because they have these forces. So it's going to take less energy to turn them into solids. So the freezing point is going to be higher. Does that make sense, guys? On the other hand, it is also going to have the highest boiling point. Because what you have to do is you have these strong forces that are keeping the molecules together. You got to put more energy in to break them apart. Are we good with that concept, guys? Because right now we're going to get into vaporization. Somebody yell at me about an hour from now so that I can take a break for you guys. Now, if you have water in an open container, Jordan, you have water in an open container. What happens?
What do you mean? It like the room temperature.
You put a glass of water out out in your porch right now. You come back at 5 o'clock. Is the water still going to be there?
Yes.
You think?
Yeah, but it's going to be hot.
You don't think the water's all going to evaporate away? Have you
Well-
ever seen where you've left water out and you come back and there's less water?
Honestly, no. Honestly.
Has anybody else seen that? It may take a long time, but if you sit and leave a glass of water out,
Slowly evaporate over
it
time.
slowly evaporates. Now, what factors affect the rate of vaporization, do you think?
Heat.
Heat is one of them. What else will do it?
Pressure.
Pressure, good. The
Yeah.
atmospheric pressure is going to affect it. What else?
Sorry, excuse me. Is the presentation supposed to be like on the shared screen right now? Because it's still
Thank you.
on.
Thank you for drawing my
that's for me.
attention to that. Nothing has really happened so far. So what are factors? We already know pressure, because if there's less pressure, it's going to be easier to evaporate the water away. We also said temperature. What else is going to affect it? How about the surface tension of the liquid itself?
Is it like surface area?
Surface area, yes. Surface area will affect it. And the intermolecular forces or the surface tension. If the liquid has a stronger intermolecular force, then it's going to take more energy to evaporate that away. We agreed with that. Are we good? Thank you. Now, there is something called the heat of vaporization. And by definition, it is the energy needed to vaporize 1 mole of liquid to gas. Basically, It's the energy needed to overcome the intermolecular forces of the liquid. Problem. Heat of vaporization of ethanol, C2H6O, is 38.6 kilograms. How much energy does it take to completely turn 55.6 grams of ethanol from a liquid into a gas? If you know nothing except dimensional analysis, you can solve this problem. Leonardo. I want energy. I want the energy. That's what the problem is asking for me for, right, Leonardo?
Yeah.
All right. I have a heat of vaporization whose labels is kilojoules per mole. And I have a grams of ethanol, and I have the molecular formula. How am I going to solve this problem?
Change the grams to moles.
Change the grams to moles. I'm going to get the 12.01, multiply that by 2. I'm going to take 1.01, multiply that by 6, and the 16.00. I'm going to add all those numbers up. And let's see, 24, so it gives me 46 approximately. And I'm going to multiply my 55.6 by 46 grams. I'm sorry, 1 mole over 46 grams. And that will give me my number of moles. Now, what do I do, Leonardo? I've got moles.
I don't know what to do after that. I'm sorry.
Okay, fair enough. Somebody else out there. If I have a heat of vaporization, which is in kilojoules per mole, and I now know the moles of ethanol,
You multiply?
all I got to do is multiply the moles by the kilojoules per mole, and I'm going to come up with my answer. Again, this is not a difficult problem. All we got to do is think dimensional analysis. I have a term kilojoules per mole. I want to end up with kilojoules. So somehow I got to multiply the kilojoules per mole by moles to get the kilojoules. I have grams of ethanol. I know what the formula is. I can get the moles of ethanol. I then simply multiply the two by themselves and I get the energy. Questions? You good?
I do. On the test, will you give us the molar mass of whatever it is you want us to find, or should we like do
I
like
will,
that
I will
ourselves?
give you the atomic masses. It depends, Manuel. All right. It
Okay.
depends upon my confidence in your ability to be able to come up with molecular weights. All right. Does that make sense to you?
Yep. Thank you.
If like after the
guess-
first test, I'm fairly confident everybody has a good understanding of how to get molecular weights, then I don't need to test you on that anymore. And I'll just give you the molecular weight because there's no sense of wasting time. Okay. Fair enough answer?
I guess since
Yes.
technically the exams are open, no, I mean, you could just bring periodic table in there anyways.
I generally speaking, Ethan, I give you a periodic table.
Oh, okay.
It's inconvenient. It's very inconvenient because of the test. You have to scroll down to it, then scroll back. So it's a pain in the butt, I will admit, but it's the only way I can give you a periodic table in a test of that nature. Generally speaking, I've tried to fix that by putting the atomic weights in the question itself.
Can I use my own periodic table?
Okay.
Yes. You're allowed, remember what I said, open book. You're allowed to have anything except another browser, your cell phone, or talking to another person.
So we can use the PowerPoints to help?
No. How are you
No.
going to get the PowerPoints without, excuse me, let me back on that. If you print them, yes.
Okay.
But if you're just trying to use them in another browser, Honor lock will flag you.
Okay.
Okay? Fair enough?
Yeah.
If you apply 26 kilojoules of energy to 43.7 grams of ice, would you have any ice left? Let me go this slideshow wise. Damn it. Sorry, something's in my way. Ugh. Don't you love technology? Okay. All right. You can solve this problem in two ways. I chose to go about it one way. Can anybody make a suggestion as to how you would answer this question?
I would personally say first we would change the grams into moles and then divide the kilojoules over the moles.
Divide?
Yeah.
If I divide the kilojoules per mole by mole, my answer would be kilojoules per mole squared. Right?
Yeah.
So are you going to divide?
No, then you would end up multiplying.
So what I'm going to do, I know that it's water, ice water, okay? I know that water has a molecular weight of 18.02. I'm going to divide my 43.7 or multiply by 1 mole over 18.02 grams to get the moles of ice. Then I'm going to multiply this. What will that give me?
Wait, you're multiplying the 18.02 by the grams?
No, I'm dividing.
Oh, sorry, dividing. Okay.
I'm dividing the 18.02 into the 43.7. I'm multiplying 43.7 grams by 1 mole over 18.02 to get the moles of ice. Then I'm multiplying the moles of ice by 6.02 kilojoules per mole to get an energy. What is that energy?
I got 14.6. Oh,
Okay, 14.06. But what is it? What is the 14.6 kilojoules? What's it
Is
the
it-
energy to do?
The amount of energy needed to melt the ice,
How much energy did I have?
26.
Did I have enough energy to melt all the ice?
Yes.
So is there any ice left?
No.
Did everybody follow that?
No, I didn't follow. I'm not gonna lie.
Okay. We'll go through the actual numbers, Anaya.
Thank you.
I got 43.7 grams. I multiply that by 1 mole over the 18 grams to get the moles of ice. I then know that the heat of fusion is 6.02. I did this a different way. Let me go back here. As I said, sometimes you can solve problems two different ways. Okay, so I have 2.43 moles. I multiply that by 6.02 kilojoules per mole. And this is 14.6 kilojoules. That is all the energy it takes to melt all the ice. Do we understand that part? Now, I had 26.2 kilojoules. Did I have enough energy to melt all the ice? Anaya? If I needed 14.6 to melt all the ice and I had 26.2, did I have enough? So if I had enough energy, is there any ice left?
No.
That's the answer.
Okay, thank you.
The way I solved it was I first made moles of ice. Then what I did was I took my energy that I had and I determined how many moles that could melt. So I divided it by my heat of fusion. I took my 26 kilojoules and multiplied it by 1 mole over 6.02 kilojoules. I could melt 4.31. I only had to have enough energy to melt 2.43. So therefore, there was no ice left. Either way, there are different ways to attack problems. All right. Would you expect NH3 to have a higher or lower heat of vaporization than SbH3?
I would
So
say
thank you.
higher because it has a nitrogen, so it would make a hydrogen bond.
Absolutely. Nitrogen to hydrogen has hydrogen bonding. SbH3 only has dipole bonding. So NH3 has larger intermolecular forces. So it's going to take a higher heat of vaporization than sp3. Good answer, Jenna. So basically, this is to illustrate that point. I have water, which has a bigger hydrogen bonding content than rubbing alcohol, which is compared to a dipole in acetone, which is compared to a diethyl ether, which only has dispersion. If you look at that, water, hydrogen bonding, the biggest hydrogen bonding, it has a very high heat of vaporization. Even alcohol is real close to it. Dipole is going to be less. Diethyl ether is even less than that. Now, we've been talking so far about just leaving the glass of water in the open air. If I put a cork in it, and some of you would like me to put a cork in it right now. If I put a cork in it, what's happening? If I leave it open, eventually all the liquid will go away. If I close the flask off, at first, there are no liquid molecules, whatever's making up the liquid, there are no liquid molecules that have been made in the gas. So the first thing that happens is we get everything going in one direction. The liquid molecules are being made into gas molecules. As it continues, the rate of evaporation is greater than the rate of condensation because we don't have enough of the liquid in the gas phase at that point. Eventually, though, we will reach a point called equilibrium in which the rate of evaporation is going to equal the rate of condensation. Whenever you have one rate equal to another rate, it's called an equilibrium. And we're going to get into this 3 chapters from now. But for right now, I just need you to understand when you have a closed system, eventually what will happen is you will increase the amount of molecules that were liquid, you will increase those molecules going into the gas phase until you reach a certain pressure. Once you reach that certain pressure, it becomes an equilibrium. Condensation equals evaporation. So what's happening? My rate of evaporation is going to stay the same. Because I don't have that many, at first, because I don't have that many molecules in the atmosphere, my rate of condensation is real low. But as the amount of the molecules get gasified, the rate is going up to the point where it reaches the rate of evaporation. From that point on, I have a dynamic equilibrium. The pressure at dynamic equilibrium is called the vapor pressure by definition. Vapor pressure is the pressure at which the rate of condensation equals the rate of evaporation. Now, if we change the system, we change the equilibrium. If we start off with a dynamic equilibrium and I move the piston up, I now have decreased the pressure because I've increased the volume. Boyle's law, straight up. If I have decreased the pressure, then what happens is I have a greater rate of evaporation than condensation until I reach the vapor pressure again. Once I reach the vapor pressure, I'm back to equilibrium. On the other hand, if I decrease the piston, I have increased the pressure, which means I am going to get a higher rate of condensation. Again, until I reach the vapor pressure level. At that time, I have got an equilibrium again. Questions, guys? Okay, can I ask you a question? Do you feel more comfortable if the temperature is 40 degrees with 60% humidity, or do you feel more comfortable when it's 80 degrees with 60% humidity?
Is that Fahrenheit?
Yeah, it doesn't matter, centigrade, Fahrenheit. Which do you feel more comfortable in? When the temperature's higher or lower?
Lower.
Say lower.
Okay, that's because there is a little less water in the air. Now, because of that, the vapor pressure is going to depend on the temperature and the intermolecular forces. This is because the temperature is going to make the more energy we put in the system, the more liquid we're going to put up into the air. And it's going to depend upon the intermolecular forces, because the stronger the intermolecular forces, it's going to want to be a liquid. It's going to want to stay a liquid longer. So the relationship between temperature and forces results in something called the Clausius-Clapeyron equation, which is the pressure of the vapor is equal to a constant times the natural log, the E figure, raised to the minus heat of vaporization divided by RT. Get used to this, guys. Get used to what's going to happen in a second, because it's going to happen throughout the rest of this semester. Can you measure pressure, guys? Can you physically measure pressure? Thank
Yeah.
you. Somebody needs to be my yes person. Yes, you can measure pressure. Can you measure temperature?
Yes.
All right. Beta is a constant. Beta is a constant, and the heat of vaporization is a constant. So, I'm sorry, back off, sorry. Beta is a constant and R is a constant. Beta and R are constants. I can measure T and P. So if I can measure T and P, and I can manipulate this formula to be the equation of a line, then it's a simple matter of getting a slope, and I can find heat of vaporization. I can't directly measure heat of vaporization, but what I can do is I can measure pressure and temperature. So if I manipulate this equation, going from the equation you see here, by taking the log, the natural log of both sides. If I take the natural log of both sides, what happens is this equation develops into this one. And the ln of the pressure of vaporization is equal to the negative the heat of vaporization over R times 1 over T plus the ln of a constant that is related to the gas we're talking about. Look, guys, Y is equal to M X plus B. I have the equation of a line here. So if I plot on a graph ln of P in the y-axis versus 1 over T in the x, if I plot that, I'm going to get a straight line, and the straight line I get is going to be equal to the negative, the heat of vaporization divided by R. To identify everything that's within this equation, P vaporization is the vaporization pressure. Heat of vaporization is the heat of vaporization. T is the temperature. B is a constant that depends on the gas. You have to note, R is a constant. It is the gas constant, but the label is different. Instead of being liter atmospheres per degree Kelvin mole, what R is joules per mole K. If you change the label of R, you change the number. So we now are going to have a different value for R because we have a different label. And R is equal to 8.314 joules per mole.
For the temperature, will that be in
Kelvin.
Kelvin? Okay.
It's anytime. First of all, this is a good rule of thumb. If you see temperature by itself, use Kelvin. If you see a subtraction or an addition of temperatures, no, I'm sorry, let me back off on it. If you see a subtraction of temperatures, you can use Celsius. That's a general good rule of thumb. If you subtract the temperatures, you can use Celsius. So if I do a plot, since my negative delta H vape over R is equal to the slope, all I have to do is plot out my slope, get the equation of the line that forms. I look at what my slope value is. My slope value here is negative 4288. That is equal to negative delta H vape divided by R. So what you're going to do is you are going to take the slope and multiply it by negative R. You will get the heat of vaporization. Understand, vaporizing things is an endothermic process. So the heat of vaporization will always be a positive number. Questions on that?
Professor, I didn't get that at all.
Okay. Natalie, do you see the equation? I don't care if you understand how it got converted from the original equation. Just do you see this equation? All right. Now, if I make LNP of vaporization a variable, if I call it Y, all right, so this LNP vape is now Y. If I make my other variable 1 over T, so 1 over T is now X. Whatever is in front of X is going to be equal to my M, which is the slope of the line. So in this case, negative delta H vape over R is equal to my slope. And this other thing is, by the way, Natalie, I can hear you, I can see your lips moving, but I'm not hearing anything because you're muted.
Yeah, I understand. I get it.
You got it now?
Yes.
So if we are able to do the slope, if we're able to get a line and get the slope of that, we know immediately what the heat of vaporization is by multiplying the slope by negative R.
Gotcha. Okay.
The other thing you need to note here, every graph that plots ln of P versus 1 over T is going to be slanted in this direction because it has a negative slope.
Thank you.
Now, the Clausius-Clapeyron equation, 2-point form. If I have two sets of value, I can literally subtract one of these equations from the other. If I subtract one from the other, I can take my first set of values, which I'm going to say is P1 and T1. If I subtract it, I get the ln of P1 minus the ln of P2 is equal to minus delta H vape over R times 1 over T1 minus 1 over T2. My LNBs go away because I'm subtracting them away from one another. So that's how this form goes into the 2-point form. Did you understand the conversion? Or if you didn't understand the conversion, did you not care? All right, I can go with don't care. The thing you have to note about this, I don't care which form of the equation you use. Note, the ln of P1 over P2 is equal to negative delta H vape over divided by R times 1 over T1 minus 1 over T2. Note the positions of the P and the T. This equation is the same thing as the ln of P2 over P1 minus delta H vape over R times 1 over T2 minus 1 over T1. Notice all I did was switch the T's and switch the P's. Mathematically, they are the same. If I switch only one of them, in this case, I've switched the T's. If I change this negative sign to a positive, it's also mathematically the same. I went through that big whole explanation for one purpose. Sometimes some books are going to use this equation. Some are going to use this equation. Some are going to use this equation. It doesn't matter which equation you use. Pick one. Pick one equation and stick with it. Did everybody understand what I just said there? I need you to hit me with the sign up. What is it? More? Where's that thing at? You guys have the ability to, yeah, thank you. Give me a thumbs up, Benita. Are you understanding it, Benita? Thank you. Emily, Jordan, Manuel, Danny, why aren't you on visual? Gianna, Araceli, you understand it? Gianna?
Yes.
Danny?
Yeah, the thumbs go away for a couple of seconds.
Sorry. Danny? Are you there, Danny?
Yes, sir.
Okay, why visualize yourself? Thank you.
All right, I will turn it on.
I need you to be in visual. All right. Sorry, I gotta get back to this. And I think I may have missed something on this. No. So, if the temperature goes up, what happens to the pressure? It's the exact question I asked in the quiz. Again, logically working through the equation. If T2 is bigger than T1, then I am dividing by a bigger number. So T2 bigger than T1, this part of the equation is going to be negative. I'm multiplying a negative times a negative. The whole right-hand side of this equation is a positive. The way I get a positive number when I'm dealing with logs is that the ratio has to be greater than 1. If the ratio is greater than 1, then P2 has to be bigger than P1. And it makes sense because the bigger the temperature, the higher the vapor pressure. Benzene has a heat of vaporization of 30.72 and a boiling point of 80.1 centigrade. At what temperature does benzene boil when the external pressure is 445 torr? There's a trick to these questions, guys. You have to understand that when something is boiling, the definition of boiling is when the vapor pressure equals atmospheric pressure. What is atmospheric pressure, guys?
In this case, it's 445.
400?
torr.
No, it's not.
Are you asking what it's equal to?
What is the pressure at the boiling point? What's atmospheric pressure, guys?
Oh, wait, it's just 1 ATM.
1 ATM, or
Like 7.
since it's in torr, use the 760.
Okay.
Okay, so now I know what the vapor pressure is at 81.C. The question is asking me, what temperature does benzene boil at? In other words, what's the vapor pressure when the external pressure is, or what's temperature does it boil at when the vapor pressure is 445? All I got to do is plug in the numbers. I've got the two pressures. There's the problem. I have the two pressures. I know that 80.1, my pressure is 760, and the other pressure is going to be 445. So Manuel, what do you want to be the P1?
Wait, I'm sorry. Where did you get 60 from?
760?
Oh yeah, 760 from the ATM. You're right.
So
So
the
Manuel,
conversion.
what do you want to be P1? 760 or 445? Choose 445.
okay,
This
445.
is, yeah, this is entirely your independent choice, right?
Yes.
All right. So my P1 is going to be P1 is going to be 445. My P2 is going to be 80.1. So I got to plug the values in here. So into my equation, I'm going to plug in 4045 as my P1, 760 as my P2. That's equal to, there's something you got to do. There's another trick. Write this down. Just say CC equation trick and highlight it. Heat of vaporization is in kilojoules. R is in joules. So to cancel them out, I either need to change my 8.314 from joules to kilojoules, or I have to take my 30.72 and change it from kilojoules into joules.
Can you repeat that?
Heat of vaporization label is in kilojoules per mole. The value for R is in joules per mole when it's 8.314. So in order to get the joules to cancel, I either have to multiply my heat of vaporization by 1,000 joules over 1 kilojoule, or I have to multiply my 8.314 joules per mole by 1 kilojoule over 1,000 joules. You have to convert either R to kilojoules, or you have to convert heat of vaporization to joules. Now, my second part of this, 1 over T2 is equal to 1 over 353.3, 353.3. And all I did there was multiply or add my 80.1 and 273.15. So I divide this number by this number, I get a negative 3695 times 10 to the third Kelvin, 1 over Kelvin, multiplied by 1 over T2 minus 1 divided by 353.3 is 283.13. Understand, this is the 80.1. I'm relating that to the atmospheric pressure of 760. All right. Be careful about your signs when you're doing this. All right. My ln of a number less than 1 is going to be a negative number. So all you got to do is hit the ln button, plug in the 0.586. I'm going to end up with a negative 5.34. That's equal to, if I multiply this number by 1 over T2, that ends up being a negative 3.695 times 10 to the third over T2. I multiply this big number by this real small number, and I get a negative times a negative plus 10.5. Subtract 10.5 from both sides, I get 15.8. A negative 15.8, that's equal to a negative 3.695 times 10 to the 3. Multiply both sides by T2 and divide by 15.8. I end up with 234K. Now, evaluate your answer. my pressure was less. My vapor pressure was less. So should I expect my temperature to also be less? If that is the case, I compare. I started off with 353. I now have 234. It is less. It makes sense. Questions, ladies and gentlemen?
Wait, where did you get the 10.5?
I multiplied negative 3.695 times 10 to the third. I did a distribution. I multiplied this by 1 over T2. I also multiplied it by the negative 2.83 times 10 to the minus 3.
Okay, thank you.
Do we have to put a negative one? Like there's a negative one after the negative 30.72 kilojoules per mole.
Wait. There's a negative.
Negative one. I don't know if it's part of the equation.
Where are we talking about the negative in front of this?
No, the first part. When we started.
All right, do you see where my the 3.695, there's a negative, or are you talking about the 30.72?
72. When we plug.
It's part of the equation. The original equation has a negative value.
In this example, you'll learn how to use a two.
No, she means there's a, after that on the other equation, there's a -1 after the 30.72.
Yes.
Right before the division.
No, that's moles to the -1.
Oh.
That's kilojoules per mole. If you'd like, I can do this. Does that make more sense?
Yes.
So that's what that meant. That meant kilojoules per mole.
This Clapeyron equation to predict the vapor pressure of a liquid at a given
Whoever's got the video on. If you've got a video on, I'm sorry, it is distracting. I want to stop share for a second. And I want to go to the other slideshow. Okay, another form of the question. First question, I was asking what the temperature was if the vapor pressure was another number other than 760. This is a different question. Boiling point of acetone is 56 degrees centigrade. What is the vapor pressure at 56 centigrade for acetone? Who was paying attention? If the boiling point of acetone is 56 degrees, what is its vapor pressure?
760 torr.
760 torr. So I'm relating the 56 that I'm going to turn to Kelvin to the 760. What it's asking me is, what is the vapor pressure of acetone at 100 degrees Celsius? Again, I'm going to use my overall equation. I know what T1 is. I know what T2 is. I know what R is. I need delta H vape. That must be given. And for acetone, it's 31.27 kilojoules per mole. I also realize that at the boiling point, the pressure is equal to atmospheric pressure. So P1 is equal to 760 torr. I plug my values in. The ln of P2 divided by 760, which is the atmospheric pressure, is equal to negative heat of vaporization divided by my R changed to kilojoules. This gets multiplied by 1 over T2, which was my 100 degrees Celsius. Convert that to Kelvin, I get 373. Minus my boiling point was at 56. 56 and 273 is 329. Doing the math. I get the ln of P2 over 760 is equal to this big honking number divided by this little number times this thing. I do this math out. This is a negative number multiplied by a negative number. My answer is a positive number. Critical point here, guys. You have to understand that this is the ln of P1 over P2. This is not the ln of P1 divided by 760. This is the ln of P1 divided by 760. So when I get to this point in the equation, I'm going to need to raise both sides e to that power. When I raise e to a log power, natural log power, the e to the ln goes away, and this becomes a normal number. So when I went from this equation to the next equation, I just took e to the ln of that value. When you take e raised to an ln, e to the ln by definition is equal to 1. So that changes that expression to P1 over 760 is equal to e to the plus 135. All I got to do is take my calculation, hit the E button, type in positive 1.35. That ends up being a positive 3.86. I then multiply 760 by 3.86, and I get 2,930 torr.
The natural log cancels out the ln.
Yes. Okay, let me do this. Hopefully I can write this. I'm sorry. That is a mathematical true statement. If you have e raised to an ln power, so if you want to get rid of a log to solve for a variable, you have to raise e to that ln value. E to the ln goes away as 1. You're left with what's left on the top there. Does that make sense to you? Now, does this answer make sense? We went from 56 degrees to 100 degrees. At 56, the pressure was 760. Do we expect the pressure to increase when we raise the temperature to 100? Gianna,
Yes.
I need you to visualize. Does that make sense, guys? I need answers.
Yeah.
31.27.
What's that?
Where did you get the 31.27 kilojoules?
That's the heat of vaporization
Oh,
of acetone.
okay.
Remember when I started to set up the problem, I said, do you know all this stuff? You need the delta heat of vaporization. It must be given. I gave it to you at that point.
Okay.
Questions, guys? Look over these two problems. Understand how to convert logs back and forth.
So the temperature increased, so the pressure increased.
Exactly. Exactly, Sam. Can everybody see the blue slideshow again?
Yep.
Do you want a 5-minute at this point or not?
Yes.
Yes.
All right.
Yeah.
My computer reads 11:10. I'm going to get a cup of coffee. When I come back, it'll read 11:15. I can. Hey, guys. How we doing? We back?
Yes.
Okay, good, 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 good. Okay, how are you feeling about that equation? There are, I'm going to stop share for a second. If you're not that comfortable with them and you need more practice, then I would go to the module. And if you go to the extra problems, there are extra problems on the Clausius-Clapeyron equation with the answers. Okay? If you need more practice, that's where you get it. And I'm sure I have at least one problem in the Pearson homework. Okay? Okay. I don't have a life, guys. I do something silly like watch water boil. Actually, it's because I'm too impatient for my pasta water to be ready. So, if you sit there and watch water boiling, have you ever noticed there are kind of like these real little tiny bubbles that at first go up and give you that kind of like false boiling? It's like, oh, good. I'm just about ready to boil. And then it takes forever after that. What you're actually doing is you are evaporating the gases that are dissolved in the water. That's what's happening at first. Then you get this kind of like water bubbles collecting in the bottom, and as they're going up, the bubbles burst. And it keeps on getting closer and closer until we get to the point where the bubbles break away from the surface and go into the atmosphere. That is literally what is happening when we are boiling. We have now succeeded in adding enough energy to the liquid to the point where it can break through and break away from those intermolecular forces and become gases. At that point, the vapor pressure has equaled the external pressure. We are at boiling point. This is when when we're at a boiling point temperature. This is why we can relate that to being 760 torr. Now, the energies of phase changes. They result from not only the type of substance, but the amount of that substance. Do you remember in Chem 1? By the way, I took a slight survey. Everybody hated thermochemistry in Chem 1. Is that true, guys? Is that true for you as well?
Yes. I hated it.
Yes.
Do you remember the equation, though? Do you remember the equation? Q is equal to MC delta T. We're going to be using it again here, guys. Okay? If we look at what's called a heating curve for 1 mole of water at 1 atmosphere pressure, what we have is something that looks like this. We get a slanted line followed by a straight line, a straight horizontal line, followed by another slanted line, followed by another straight horizontal line, followed by another slanted line. This is what is happening. Now, why do you think there are sloping and flat regions to the curve? Anybody offer anything?
Oh, wait, what? Why there's like
Why do
sloping
we have,
regions?
why do we have slanty parts and flat lines? Slanty parts and flat lines. Do you have any idea why?
The slanted parts are just represent the like increase in thermal energy, like, and
That's exactly
when
right. We're in one phase. When we're down here, this is water, right? What's water exist at below 0 degrees? Come on, guys.
Nice.
Ice. Thank you. It's involving ice. Now, what is happening is if we're at ice at minus 25, and I eventually want to get to steam, I'm going to have to heat that ice up. So all the energy that's getting put into my system at this point is being put into making that temperature go up from minus 25 to 0. Does it make sense? Now, at 0, what is happening is I need to change from ice to water. So all my energy, every bit of my energy is going to be put into making that ice into water. So I'm not putting any energy into raising the temperature, so the temperature stays constant. That's why we get these horizontal flat lines. And it's only when I've converted all of my ice to water that that temperature can start going up again. And it continues going up until I reach the boiling point, at which time all the energy is going into breaking the intermolecular forces that make something a liquid. So all this energy is going into turning something from a liquid into a gas. And at this point, after all the molecules become a gas, I can start to heat it up again, which is why it is much more dangerous to be burned by steam than it is by boiling water. Boiling water, we at least know it's only at 100 degrees. Steam, you have no idea what temperature it is. So when I am going on a slanty line, my energy is going to be equal to a formula. The slanty lines, the energy is going to be equal to the mass of the substance times the specific heat times the change in temperature, T final minus T initial. That is important, guys. You need to, again, keep track of your signs here. So when I'm in a slanty line, it's going to be mass times the specific heat times the change in temperature. In this case, to go from minus 25 to 0, my final temperature is 0 minus a negative 25. So I have to add 25 degrees to get that to effect. Do not need to use Kelvin here. We're subtracting one temperature from another. If you add 273 to 25, you also have to add it to 0. When you subtract it out, that 273 goes away anyway. All slanty lines have that same formula. Q is equal to ms delta t. You may have heard it as MC delta t or MCAT. Now, when I am on the flat lines, oh, one more thing I need to mention about the slanty lines. The specific heat of ice is different from the specific heat of water, which is different from the specific heat of steam. Just keep that in mind. Now, if I'm on a flat line, we've already done that equation. We've already done that one. Remember way back when we did, 1 second. Remember this problem? All we're doing right here is we're taking something at the boiling temperature of ethanol, and we're taking it from liquid ethanol to a gas. That is the same equation we're going to use here. We're going to use the heat of vaporization times the moles of our substance. That will give the energy. Now, again, do I have to input energy to take something from a liquid to a gas? Come on, guys.
Yes.
Yes.
Yes, I do. So if I have to input energy going in this direction, this flat line is going to be a positive number. This flat line is going to be a positive number. So if I'm going from ice to water, my energy used is going to be positive. If I'm going from water to steam, the energy is going to be positive. On the other hand, if I am going in the opposite direction, if I'm going from steam to ice, going from a gas to a liquid, I have to take energy away. If I'm taking energy away, that is going to be a negative number. Again, I'm only talking about the flatlands here. If I'm going down the curve, the flatlands are going to be negative. If I'm going up the curve, the flatlands are going to be positive. So let's think about what's happening. I am taking 1 mole of water. Let's see. See what the original question, don't do that. No. You've confused the hell out of me now. I'm taking 1 mole of water at 1 atmosphere. So if I'm starting at 1 mole at 25 degrees below zero, I need to get that to 0. So the first part of my curve is my energy, Q, is equal to my mass of my water. 1 mole of water is 18.02 grams times the specific heat of water times my T final minus T initial. If I'm starting at minus 25, ending at 0, this is going to be 0 minus a negative 25. I've reached the flat part of my journey. At this point, my energy, I need to input it to get from ice to liquid. I'm going to take the heat of fusion times the number of moles. So I'm going to take moles times the heat of fusion. Again, I am going from ice to liquid, so this number is going to be positive. Next part of my curve, I've completed all of my, I've converted all my ice to liquid. I now need to take my liquid from 0 up to 100 degrees. Again, I'm going to use the same formula I did before. Q is equal to M times the specific heat of water now, times final temperature is 100 minus 0. I'm going to have my 100 minus 0 is going to be a positive number. So that when I do this equation, that's going to take care of the sign. I've reached this point. At this point, I'm turning all my water into steam. I need to multiply my heat of vaporization times my moles of steam. Again, I'm going from water to steam. I need to input energy. This number is a positive. Last part of the curve. I am going from steam at 100 degrees to steam at 125. Again, I'm going to use the Q is equal to MC delta T. My mass is 18.01. The C is going to be my heat of vaporization of water times 125 minus 100. Yes, this is a pain in the ass. How long do you think it would take you to go from minus 25 up to 125? Don't worry about it. You can demonstrate everything you know by taking something like something at liquid to something at steam. You'll demonstrate all the things there. So I'm not going to make you to do the entire curve. I'll make you do a portion of the curve. Like this problem. How much heat does it take to raise the temperature of 25 grams of water from 55 centigrade to 150 C? What am I starting at? Where am I starting at the curve? Section 1, 2, 3, 4, or 5? Jana. Let me look at the problem. The problem is I have 25 grams of water. I need to go from 55 C to 150 C. What is water at 55 degrees Celsius?
Liquid.
Liquid. Jana, be confident in your answer. You're right. Be confident. So I'm water. I'm at stage 3. Okay, Araceli. When water is 150 degrees, what stage of the curve am I at?
Is it in the gases part? Like when it's like already
1, 2, 3, 4, or 5?
5.
5. Only I'm a little bit beyond here because I'm at 150 degrees, right? So when I'm in the liquid phase, or when I'm in the steam phase, I'm going to use the Q is equal to MC delta T. When I'm on a flat line, I'm going to either use the heat of vaporization or the heat of fusion times the moles. So, anybody want to try it before I pick somebody? I've already picked on manual once. Let's see who's at the bottom. Sakari, am I pronouncing that correct?
It's Sachari.
Sachari, I'm sorry, Sachari.
That's fine.
Sachari, I need to raise 25 grams of water from 55 C to steam at 150. My strategy is I'm going to try and find out how much energy it takes to go from 55 to 100. Then I'm going to find out how much it takes to go from 100 degrees of liquid of water to 100 degrees of steam. Then I am going to do a third section to do my energy needed to take it from 100 degrees of steam to 150. So can you tell me how to set up the first stage of this?
Yes, give me one moment.
Saturi, I'm gonna have
Yeah.
to,
No, I'm sorry. It's because someone kept calling me, so my laptop kept showing that. But so are you gonna change T between the 55 and the 100 degrees Celsius?
I'm gonna change my delta T to my final temperature is 100. I'm gonna subtract my initial temperature, which is 55. Okay? What else do I have to do to that?
Does it have to do with the difference between liquid and steam?
Nope. What did I say? I said we're on the slanty line, right?
Yes.
What was the formula I told you to use for the slanty lines?
Is that the Q one?
They're both Q.
I mean the Q equals the MC, the MC S, I think it was.
MC delta T.
Yes, that one.
Okay. So the problem gives me the mass and the curve gives me the final temperature. The problem gives me the initial temperature. So the way I'm going to set that up is I'm going to put Q is equal to MC delta T. I've got the 25 grams. My specific heat of water is going to be 4.18 joules per gram centigrade times my change in temperature. This gives me 4703 joules. I'm going to either have to convert joules to kilojoules or kilojoules to joules. I'm just going to go ahead and do it at this point. And I do that by doing 1 kilojoule over 1,000 joules. Again, this number is positive. So overall, my energy here is a positive number. Okay? Valeria. Saturi has now taken us from 55 up to 100. What I want you to do is tell me how much energy on our journey it's going to take us to go from liquid to steam. Do you remember how we did that?
No.
Did you say no, Valerian?
Yeah, I said no.
I don't know is a great answer. I bothered Leonardo at one point. Let's see who else is out there. Emily.
So you have to use the other equation, the Q equals N and then heat of vaporization.
N is equal to, Q is equal to N, the number of moles, times my heat of vaporization. So I have 25 grams, Emily. What do I have to do with that 25 grams of water?
Turn it into moles.
By multiplying by 1 mole over 18.02. So that is going to be my second equation. Again, the heat of vaporization is in kilojoules. That's why we changed the other one to joules. So 25 divided by 18.02 gives me 1.39 moles. The 1.39 moles times 40.5 kilojoules per mole gives me 56.2 kilojoules. I'm going from water to steam. Do I have to put energy in or do I have to take energy away?
Put energy in.
Put energy in. Putting energy in is endo-exothermic.
Endothermic.
The sign for endothermic is positive or negative?
Positive.
That is why, where are we at? Here. That is why when I finally ended up the number, that number was positive.
I have a question.
Yep,
Is the heat of vaporization for water, is that given or do we
it will be
calculate?
given, yes.
Oh, given, okay.
It's a constant, Benita.
Okay, thank you.
Thank you for asking the question, Benita, because I was looking for a volunteer to do the last part.
Oh.
The problem says we're going from 55 to 150. So again, we already agreed that we are on another slanty line, right, Benita? We're going from 100 to 150. So we're on this slanty line, right?
Okay.
So which equation are we going to use?
The same one that we used, the Q equals M times C and delta T.
Exactly. Only this time we're going to use the specific heat of steam, which is, I believe, 2.09, if I remember correctly, 2.01. So I'm going to take the mass of my water times my specific heat. Remember, this is in joules, times my final temperature minus my initial temperature. I get 2,512 joules times 1 kilojoule over 1,000 joules, 2.55 kilojoules. Again, this thing makes this a positive sign. If you can't remember, going from ice to steam is positive on the flat lines, and going from steam to ice is negative. If you can't remember that, then just look at the delta T's. The sign of your delta T is going to be the same sign as your flatland because we're going in the same direction. Last step for this, I got to add all three. I get 4.05 plus 56.2 plus 2.55. I end up with 62.8. Remember, the heat capacities, the C labels are joules. When you're dealing with the delta H's, they're in kilojoules. So you have to convert one to the other. Are we good, ladies and gentlemen?
Is the 4.05 from the first part?
Yes.
In the PowerPoint it says 4.703.
Okay.
Is that a different number?
I corrected it in one. Which one's correct, guys? I don't have my calculator with me. Which one's right? All you got to do is multiply 25 by 4.18 by 45.
The 4.703 is the correct one.
Okay, so now that is 61.1, 61.1, 63.6, 63.7. I did that in my head, so is that right or wrong, guys? Right or wrong? Am I right?
Yeah.
Come on, I like to be told I'm right.
Yeah.
It makes
Yes,
my
you're
whole
right.
day. Are we fairly good about this? If you want more problems, if you want to see how more problems are solved, again, I'm going to stop sharing this for a second and go to the other PowerPoint. I go through an entire, again, this is a pain because I take it from $25 grams of ethanol at 100 degrees. This is supposed to be negative, guys, negative 120 to a 123 centigrade. So I go through all 5 steps here, guys. If you want more help in that.
I have a question.
Hmm?
Is this what quiz 2 is going to be over?
The intense question is going to be on this. Less intense questions are going to be on chapter 14 because all I have to do right now is go through phase diagrams and we're done with this chapter.
So quiz 2 is gonna be over Clapeyron equation and questions over PowerPoint 14 or chapter 14. Okay.
And possibly dynamic vapor pressure and dynamic equilibrium. Okay.
So it wouldn't be a good idea to take the quiz anytime soon.
And I don't know how to answer that question.
Okay.
So I don't know how to answer it.
Okay. Well, you're saying it's over PowerPoint 14, but if we haven't gone over it, I don't want to go take the quiz.
Remember the definition of the quizzes. Half of the questions are going to be on what I covered today. The other half, I want you to read ahead, view the PowerPoints of the next PowerPoint so that you have a foundation. The questions will be easier on the material that I need to present yet. They will be easier than the questions on the material I have already presented. Yes, I know, people hate that. Okay. Right now, the next part of this is going to be interpreting graphs. And basically, you can make a graph and you can plot where it's going to be a solid, liquid, or a gas. And you can put that in graph form, and it's called a phase diagram. And basically, it's going to allow you to predict how a substance is going to respond to changes in pressure and or temperature. I've got a phase diagram of water. By the way, do you see this line that curves to the left? This is the only time you're going to see it. Because what is happening in water, what is less dense, ice or water?
Ice is less dense.
Ice is less dense than water. So literally speaking, as you increase the pressure, you're creating more ice. You're creating more water because water is less dense. Does that make sense to you? Most of these phase diagrams will have a slanted line in the other direction. This is because the liquid is more dense. And as you increase if you increase the pressure, a substance wants to relieve that pressure by becoming more compact. If it becomes more compact, then what happens is it is becoming more of a solid normally. That's not the case for water. If you add pressure to ice, you will make water. In any case, the portions of a phase diagram. We have a line that delineates between a solid and a gas. That is called the sublimation curve. Sublimation is where something goes directly from being a solid into a gas without passing through the liquid phase. Easy identification of this is dry ice. Dry ice is solid at room temperature, or solid at a certain temperature. You put it at room temperature, it doesn't even go through liquid, just goes straight to a gas. So the area between the solid and the gas is a sublimation curve. The area between the solid and the liquid is called the fusion curve. The area between the liquid and the gas is called the vaporization curve. And there is going to be a point. There will be a point where all three lines intersect. At that particular point, your substance exists in all three phases at the same time. If you do get to the right temperature and pressure, you have reached the critical point, which is the point where your sample is no longer solid, liquid, or gas, but actually becomes a plasma. That is summarized there. All right, let's deal with water first. If I am at 50 degrees Celsius and 1,000 torr, what phase am I in? Jenna?
Liquid phase.
All I got to do is kind of get an idea of where it is here. And I know that it's above 760. So I'm in that area of the graph. Rhea, I haven't talked to you yet, have I?
No.
Rhea?
No.
If I am at minus 10 degrees Celsius and I am at 800 torr, what phase am I in?
A gas.
Minus 10. So this is 0, Rhea.
Mhm.
I've got to go over to this part, right?
Yes.
Then I have to go to a point where the
solid.
solid is at about, what did I say, 800 torr?
Yes.
What phase am I in, Rhea?
Solid.
Okay, let me see who else is in here. I don't want to, no, never mind. I was going to say something. I don't want to do that. Danny. Danny. Danny, this is why I have you turn the things on. You need to be present, guys. Let's see who that. Geez, there are about 4 guys in here, and I've already asked you questions. Wait, Gianna, you here?
Yep.
You're at 150 degrees Celsius and 760 torr. What phase are you in?
Gas, or it's kind of on the line, so yeah, gas.
I said 150. You're pretty much out here. So if you were exactly at 100 and 760, you would be on the curve, right?
Mm-hmm.
So you're a little bit this way. Does that make sense, Gianna?
Yes.
Let's go to a different diagram. Who haven't I bothered yet? Parker, you want to do one real quick?
Sure.
What's the triple point at?
For which one?
We'll go with carbon dioxide.
It is at negative 56.7 degrees Celsius and 5.1 atmosphere.
That was too easy. You're at minus 90 degrees Celsius and 10 atmospheres. What's your phase?
For carbon dioxide still?
Carbon dioxide.
Solid.
Solid. Jessica?
Wait, I have a question.
Yeah.
Who's
If
waiting?
it's at the triple point, doesn't carbon dioxide can be like solid, liquid, and gas at the same time? And why is it liquid then? I
Why
mean
is it-
solid. What is he said? Why did he say solid?
That's because I asked him another question.
Oh, okay.
And I
Okay,
said,
sorry.
I think I said minus 110 atmospheres. So if it's
Okay.
minus 100, you're to the left of this point,
Right.
and 10 atmospheres get you in here. That's why it was
Yeah, I
solid.
didn't hear right. Okay, thank you.
Good. Who was that?
Natalia.
Natalia, good. Congratulations. You've earned the next quiz. The next question. You are at 200 degrees Celsius for iodine. Iodine. You're at 200 degrees Celsius and 90 atmospheres. What is it likely? What is the likely phase?
Liquid.
Liquid. Okay. Emily, have I bothered you, Emily? Have I bothered you yet today?
Yeah, but I can do it again.
Nah, these are too easy. Jordan, are you getting this?
Yes.
All right. Does anybody need me to go over this any further? I actually think that they've done a good job in teaching you guys how to read graphs. I usually don't have to do this very often. Okay. Last subject. I'm sorry I lied about the phase diagrams. Last subject we have to talk about before we leave this chapter. And we're dealing with cohesion forces, which is basically the way one molecule gets attracted to another. And the first thing I'm going to talk about is surface tension. And surface tension is nothing more than the tendency that a liquid has to minimize its surface area. Molecules at the surface of a liquid have less intermolecular forces that act on them. I'm making a statement. Does anybody want to venture a reason why?
Do they just have less molecules like interacting with them, basically? Like,
pretty much that's the answer. If I have a whole series of molecules, okay, let's look at this guy here. This guy here, doesn't he interact with the one on top and the one on left and the one on right and the one in bottom, right? Isn't that true? Now let's look at the surface of our particular thing. In a very simplistic way, it interacts with the one on the left, and it interacts with the one on the right and the one on the bottom, but there's nothing on top. So it has less force that's holding it there. Now, if it has less force, it's held looser. It's held looser to the other ones. So therefore, the molecules that are at the very surface have more energy because they're held tightly less because it doesn't have anything above it. Does that make sense to you?
Yeah.
So if the molecules at the surface have more energy, then in order to promote the molecules that are below it, you need to give them more energy, right? Since systems want to have less energy, this causes the liquid to want to reduce its surface area so that we have a force called the surface tension, which wants to minimize the surface area of the particular liquid. It decreases as intermolecular forces decrease. So Atar? Is it Atar?
Yes, it's Aether.
Atar. I'm sorry, am I even close?
You are, yes.
All right. If this statement is true, if this statement here is true, and it is, surface tension decreases as intermolecular forces decrease. Which has a greater surface tension, water or hexanes?
Is it water?
Water has hydrogen bondings. Hexane only has dispersion. Therefore, water has greater intermolecular forces. Therefore, it's going to have a greater surface tension.
Is hexane a gas?
No, hexane's a liquid.
Okay.
What happens, the more carbons you put on a chain, the more chance you have of being a liquid. Remember, the bigger the molecule, the more intermolecular force you have. So hexane is a 6-carbon chain. Something like butane, which is only a 4-carbon chain, has less intermolecular forces, so it can exist as a gas. Hexane at room temperature has 6. It has more intermolecular forces. It exists as a liquid. Another cohesive force is something called viscosity. And viscosity is nothing more than a resistance of a liquid to flow. If I look at my little circles, I'm sorry, basically because of our intermolecular forces, the molecules do want to stick together. So I get a force. There's an intermolecular force of this circle to that one and this one to this one, back and forth, all the way down the line. So if I'm at the very end and this guy wants to move to the right, he's going to pull this guy with him. And he's going to pull this guy with him and this guy with him. Now, the thing is, if there is a large amount of intermolecular force, there's going to be a resistance to that flow. The resistance to that flow is called viscosity. The greater the viscosity, the greater the intermolecular force, the greater the resistance to flow. Let's think about it. You've seen them paving roads, right? They pave roads with tar. You've seen them pour the tar out of the machine. You've also filled up with gasoline. Both of them are hydrocarbons. Which one is more viscous? Which one resists flow more? Tar or gasoline?
Tar.
So, do you think the molecules are larger in tar, or do you think they're smaller, or do you think they're smaller than gasoline?
I'm guessing larger.
They're greater.
There's more intermolecular force. Tar is more viscous, so you interpret that has greater molecular forces, which means it's going to have a larger molecule. There's another cohesive action that's very, very important. Very, very important, especially to plants. Anybody ever seen Wicked, the musical?
Yes,
Who is yes?
Jenna.
Jenna, good for you. I love musicals. Do you like musicals?
Yes, I do.
Ah, great. Now, do you remember what song they sang at the end of
Yeah.
Act 1?
Defying gravity.
Exactly. This is what capillary action is. It's the ability of a liquid to defy gravity. So how does it do it? There are two forces at work. It's consistent of the adhesion, the attraction of the liquid to the surface. and it has cohesion, the attraction of one liquid molecule to another liquid molecule. So what happens is the first little adventuresome molecule comes out and starts to attach itself a little bit higher. Well, what it does is it pulls the next one along with it, the next one along with it. So then this one goes up, attaches a little higher, pulls this one up and this one up. And that's basically how capillary action happens.
It's like they're playing like leapfrog or something.
Kind of, sort of, yeah, exactly. Exactly. Now, of the two properties, I got to sit here and I got to figure out what they are. Of the two properties, adhesion, the attraction of the liquid to the surface, or cohesion, the attraction of the liquid to itself. Which one is heterogeneous?
Adhesion.
Adhesion is heterogeneous. Yeah. Yeah, that's, like I said, it's adhesion. Okay, so basically what you're doing when they're pulling it up, they're literally saying that the force of the capillary action is greater than the force of gravity. That's why these things are able to move up the way. And the molecules continue to go up until the cohesion, until the capillary force equals the force of gravity.
Wait, sorry, I have a question. Can you go back to slide 120? Did you say the answer is adhesion?
Yeah. Adhesion, wait, I originally said cohesion.
So, because I'm looking at,
adhesion is the attraction of the liquid to the surface. So that's the hetero one. Because you've got a liquid with the surface. These molecules are different.
okay, never mind.
Is the liquid to the liquid. So that would be homogeneous.
Okay, because I'm looking at the one on Canvas and it says cohesion for that.
Yeah.
Yeah, it's okay. All
It's
right, thank you.
adhesion. It is adhesion.
Okay.
All right. Last slide. Do you remember when they were teaching you how to read volumes in a graduated cylinder? Do you remember they told you that they wanted you to read the bottom of the meniscus? And the meniscus being the U-shaped thing of that the liquid forms in a narrow tube. Do you remember that?
Yep.
Okay. In the case of water and glass, water has more. Did I do this wrong? I got to check the definitions. Guys, check these definitions in a few minutes. I may have gotten them wrong. May have somehow gotten them switched. Bottom line, the water has more attraction to the glass than it does to itself. So what happens is the water starts to creep up on the glass and it has less attraction with each other. So in effect, that's why you see the U go up on the glass and then it kind of goes down. In actuality, what you're seeing is you're seeing a cone there. You're seeing a cone where the very bottom center part of the top of the liquid is the very bottom part, and it kind of goes up and out from there. I will fix this and put it back onto the slide, because I think this interpretation is correct. Any case, guys, do you have any questions? Questions are a good place to stop.
I do have a question, but it's not about this PowerPoint. It's about
Okay.
the, yeah, it's about the homework. So the introduction one that we're supposed to do, were we supposed to do it before class? Because the due date isn't on there. It's like for July or something.
That's because it's extra credit.
Oh, it's extra credit. Okay, so that was
I
due.
wanted you, it makes sense for you to do that first. The
Right.
reason I put the date the way it is, some people have, for one reason or another, don't get to it right away. So instead of me having to go back into the homework and constantly change the dates, I just put it out that far just because of that reason.
Oh, okay, so we can still complete it?
Yeah,
Okay.
no problem with completing it.
Okay, thank you.
Anything else, ladies and gentlemen?
I have a question, but I don't
Any-
want to like everybody because it's over like something earlier in the PowerPoint.
Okay.
Okay. I'm just a little confused about the conversions because I took like I told you I had took Kim and so
What
when
talking, what general subject matter? And I,
oh it's over the sorry, it's over the equations that we did earlier, the CC equations.
the what?
The CC equations.
Okay, we're talking about these equations.
No, Classius Capron. The
Oh, the CC. I thought you said CT. Okay, guys, I have to do one thing. I have to make one caveat. I really have to keep my eye on 1220 because I literally, some of you have me in class face to face at 2 o'clock. I literally have to drive from my home in South Petersburg to Del Mabry, and I'm hoping to get there in an hour and a half. So just be aware of that. I will be leaving precisely at 12:20. Now, Anaya, I'm sorry. I will give you the attention. Now, what specifically is your question?
So when I'm doing it, when do I apply the conversion
What conversion?
from kilojoules to joules?
Right here. Okay. In order to cancel out the energy things, you have heat of vaporization is in kilojoules.
Okay.
That's the label of it.
Okay.
R is in joules. So in order to cancel the joules and the kilojoules, I have to either convert the kilojoules into joules, or I have to convert the joules into kilojoules.
Okay.
So you have to do that basically right away.
Okay. All right.
Anything else, ladies and gentlemen? Okay, Danny, are you there?
Here,
Danny, where were you?
here and not here.
All right, if I see you not here, I mark you absent.
All right.
It's like leaving the class for half an hour. Just be aware of that, all right?
Okay.
All right, ladies and gentlemen, take care. I did forget to call roll. That means you got a free day today. I won't forget it next time. Or I'll do it this way. Anybody that reminds me of roll gets an extra credit point.
All right.
Okay, ladies and gentlemen, having nothing more to say, I will stay until everybody leaves.
Oh, Professor, I do have a question on, I was working on the chapter 12 homework. And one of the questions, it asked for the vapor pressure of ethanol at 19 degrees Celsius. And it gives you, it gives you another, the normal boiling point. I got down to the point where all I have left is it's ln pressure 2 over 760. I don't know how to undo like
Well, wait,
that
didn't
part.
they give you, I thought you said that they gave you the temperature and the pressure at that point.
They gave you, it's the 2 point. They gave you 2 different points.
Yeah,
And then,
but they
except
gave,
for the,
they gave you a temperature that had a pressure in it, right?
yeah, they did.
Okay, so you take that temperature with the pressure, call it, say you want to call it T1, put the temperature in for T1 and that pressure in for T2. Then what they did was they gave you a boiling point. Correct?
Yes,
Okay, the boiling point is the temperature, right?
yes.
Put that in for T2. Now, if something is boiling, that means its vapor pressure is at 760 by definition. So the pressure at that point would be 760.
So they gave us the second one. They gave us the normal boiling point. It was the first one that doesn't have a pressure on it.
What's the question?
It's item 17.
Email me about it, okay?
Okay, I will.
I'm sorry, guys, it is 12:20 now. I promise to give you an answer. I will look at it. But I just, if you email me, that's the best way I can have of reminding myself. Okay?
Okay.
Take care, guys. We got to go.
All right.
Thank
so
you. Have a good day.
Have
I
a good
just
day.
wanna remind you about the methanol question on the quiz. I also got that one right and it said wrong. I just
Yes,
want to,
okay. Manuel,
yes,
shoot me a quick email. That will remind me to go back and check everybody's
we'll do.
to make sure it's self, okay?
Will do.
All right, take care. Manuel, I like to wait.
You're good.
I
No,
like to
I'll
wait
leave
until
right
I'm
now.
the last one in the room, okay?
I'll leave right now.
All
Bye.
right, take care.